Bismillah ar-Rahman ar-Rahim. Function f is from Rn to R. Function f is subdifferentiable at the origin. Let's recall what this means. Function f, if it is subdifferentiable at x bar, which is a point in Rn, this means that there exists some vector, let's say q, in Rn, and we say that this vector belongs to the subdifferential of function f at x bar. And this vector satisfies the following inequality. F of x is greater than or equal to f of x bar plus the inner product of this vector, so q transpose, and then x minus x bar. And this inequality is true for every x in Rn. What we are saying here is that the function f is subdifferentiable at 0 at the origin. In our case, there exists z, which is a vector in Rn, and f of x is greater than or equal to f of 0 plus z transpose times x minus 0, which is x. This inequality can be written in this way. Z transpose x minus f of x is less than or equal to minus f of 0, and this is true for every x in Rn. The Legendre-Fenchel transform of function f is minimum at 0. The Legendre-Fenchel transform, or the Fenchel conjugate of function f, is the function g of y, and y is a vector in Rn. G of y is the supremum over x in Rn of the function y transpose x minus f of x. This is the Fenchel conjugate of function f, is given by this supremum. What the problem says is that the Fenchel conjugate is minimum at the origin. This means that g of y is greater than or equal to g of 0, and this is true for every y in Rn. What is g of 0? G of 0, from the expression of the Fenchel conjugate, g of 0 means that we replace this y vector by the O0 vector, and so this inner product will be 0, and g of 0 is the supremum over x in Rn of minus f of x. Now let's go back to the red inequality here. There exists a vector z such that z transpose x minus f of x is less than or equal to minus f of 0. That was our conclusion based on the statement that the function f is subdifferentiable at the origin. Now look to the left-hand side. It resembles this term here, which we have in the definition of the Legendre-Fenchel transform of the function. So this motivates us to go to this inequality and take supremum of both sides with respect to x in Rn. If we do this, the right-hand side is not a function of x. When we take the supremum, this remains as is. The left-hand side becomes exactly the Fenchel conjugate evaluated at vector z. Thus, after taking the supremum, the left-hand side becomes g of z. Note that g of y is greater than or equal to the supremum of minus f of x for every y. So if we use this here, g of z is greater than or equal to the supremum of minus f of x, and this is with respect to x in Rn. We have the supremum of minus f is less than or equal to minus f of 0. Take this inequality, multiply both sides by minus 1. We get that f of 0 is less than or equal to minus the supremum of minus f of x over x in Rn. But minus the supremum of minus f of x, this is exactly the infimum of f of x, x in Rn. Recall that if you have a set S, which is a subset of the set of real numbers R, consider the set S bar, which is minus x, where x is in S. This means that the set S bar contains the elements of set S after multiplying each by minus 1. This is S bar. Suppose that the infimum of S is L. Then by definition of infimum, we can conclude the following. For every x in S, we have that x is greater than or equal to L. And for every epsilon that is greater than 0, there exists x tilde in S such that x tilde is strictly less than L plus epsilon. This is because the infimum is the greatest lower bound. Now, if we multiply this inequality by minus 1, we get that minus x is less than or equal to minus L. For every element in S bar, this element is upper bounded by minus L. Minus L is an upper bound on the elements of set S bar. And if we take this inequality, multiply both sides by minus 1, we get that minus x tilde, which is an element in S bar, is strictly greater than minus L minus epsilon. This means that minus L is not just an upper bound. Minus L is the least upper bound. From here, we conclude that minus L is the supremum of S bar. If we multiply both sides by minus 1, then L is equal to minus the supremum of S bar. So the infimum of S is minus the supremum of this set S bar containing the elements of S multiplied by minus 1. This is exactly what we have here. We are done. F of 0 is less than or equal to the infimum of f of x. The infimum of f of x is less than or equal to f of 0, or f evaluated at any point in Rn. So f of 0 less than or equal to the infimum less than or equal to f of 0. Then f of 0 is equal to the infimum of f of x over x in Rn. This means that f of x attains a minimum at the origin.